Hello, analysis students. Um, so I'm going to talk through in this lecture packet the Cauchy criterion. And the Cauchy criterion is a very important result in real analysis in that it gives you a way of checking if a sequence converges without needing to guess what the limit of the sequence is. And one implicit place that you should remember, a result which you should remember from Calc 2, which uses the Cauchy criterion really heavily, is the comparison test from analysis, which tells you that if all of the terms of this sequence, which all of the... Go and look up, I don't want to talk about it today, the comparison test from Calc 2. The proof of that, which we will do in this class, it'll be an optional section, but I will actually cover it. That result is true because of the Cauchy criterion. So let's go ahead and remember the closest thing we have to the Cauchy criterion right now. So right now we have one sufficient condition that tells us that certain sequences converge without having to know what the limit of the sequence is beforehand. And that's the monotone convergence theorem, which says, informally, no, this is fully formal. Oh, I need this button. If a sequence is monotone and bounded, then it converges. The goal today is to develop a new condition, which will also be a sufficient condition. So if you know, sorry, let's do it in yellow. If you know that a sequence satisfies this condition, then you will know it converges, and it will also be necessary. So unlike the monotone convergence theorem, there are lots of sequences that are not monotone, but they converge. This will give us a new condition which will be better in that it'll be necessary and sufficient. Just because you check a sequence and you find that it isn't monotone doesn't mean it doesn't converge. If you check a sequence and find that it is not Cauchy, then you know that the sequence does not converge. So, let's state this Cauchy condition. So this condition is the condition which this whole lecture is built out of. So a sequence, A sub n, is called Cauchy if for every epsilon bigger than 0, there exists a big N such that if little m is bigger than big N and little n is bigger than big N, then absolute value of A sub n minus A sub m is less than epsilon. Oops, let's put a period there. So I'm going to take this, I'm going to go off to the side, and let's write it just in formal symbology. For all epsilon bigger than 0, there exists a choice of big N such that for all m bigger than big N and n bigger than big N, absolute value of A sub m minus A sub n is less than epsilon. So let's translate that just a little bit. So this epsilon has the same job as it has in the definition of the limit, no matter what error bound you want. There exists some big N, some threshold value. There exists some threshold value that as long as you look beyond the threshold value, the terms of the sequence are within that error bound of each other. So this doesn't say that all of the terms of the sequence are getting close to a single output. It says that all of the terms of the sequence are getting close to each other. That's what it means to be Cauchy. A sequence is Cauchy if, as you look far enough along in the sequence, all of the terms of the sequence are getting close to each other. And if you view the completeness condition of real analysis, saying that everywhere that it looks like there should be a real number, there is a real number. If you see a bunch of numbers and they're all getting close to each other, they should be getting close to something in particular. That's not a proof, but that's maybe a motivation about what this has to do with completeness. So that's this idea. So here's the main goal, the Cauchy criterion for convergence. A sequence is convergent if and only if it is Cauchy. So that's what necessary and sufficient means. This if and only if. That's what necessary and sufficient means. If a sequence is convergent, then it is Cauchy. So Cauchy is a necessary condition for convergence. If a sequence is Cauchy, then it is convergent. So being Cauchy is also sufficient to conclude the sequence converges. So before I'm going to prove the theorem, and the proof of the theorem won't be so bad, it'll basically be built on top of Bolzano-Weierstrass. But just the statement of Bolzano-Weierstrass. The proof of Bolzano-Weierstrass was maybe kind of hard. We're just going to use the result. But before that, let's assume the Cauchy criterion and make an application. So here's a series, a sequence. If you want to replace this n with an infinity, you would see a series, but we haven't made that formal yet. So let's define the sequence S sub n to be the sum from k equals 0 up to n of negative 1 to the k all over 2 to the k plus 1. So there's the first couple terms of the sequence up through the kth term all the way up through the nth term. So according to the following claim, the sequence is Cauchy. If I know that this sequence is Cauchy, then I know it converges. Saying where it converges is, not terribly possible using these techniques. Maybe I'll take a pause after we prove the claim and do some computational analysis. So, claim, this sequence is Cauchy. Well, there should be another comma there. If there's a starting comma, there needs to be a second one. So let's do the proof. So, to show a sequence is Cauchy, I need to prove this. I need to prove that for every epsilon there exists a big N such that for little m and little n bigger than big N, the absolute value of a sub m minus a sub n is less than epsilon. So, this will look a lot like an epsilon n proof of convergence. We'll consider any epsilon bigger than 0. We'll let big N be something that we get to prove. We'll assume that little m and little n are bigger than big N, and we'll try to show that absolute value of s sub n minus s sub m is less than epsilon. So maybe I'll put this in blue. What do I want to show? I want to show the absolute value of s sub m minus, I'm going to say s sub n minus s sub m. It clearly doesn't matter what order I put them in. Now one of the two is bigger than the other, so woe log, I will assume that little n is bigger than little m. So armed with that, let's try to analyze the difference between these terms. I'll have to flip back and fill in my choice of big N, but just like any proof of any epsilon n proof, often you don't know the choice of big N till you're done. So let's see where you need it. So there's one proof. Ooh, no, that's... I stopped recording. Okay. Consider any epsilon bigger than 0. Then we wrote down a choice of big N. There wasn't motivation if you were just reading this from here why that's a good choice of big N, but it comes out in the wash. We then consider any little m and little n bigger than big N. This assumption doesn't lose us any generality. This assumption. This assumption. And then what to go through. So here it is. S sub n minus S sub m. By the definition of S sub m and S sub n. So maybe I'll write that. By the definition of S sub n, the sequence, we conclude that S sub n minus S sub m is this. Now you'll notice that there are a bunch of common terms. It's impossible for me to gauge how you are feeling So maybe I'll add the intermediate step that in previous semesters people have wanted, depending on how you feel about summation notation. So this first sum, well, maybe we'll color code a little bit, is the sum of the first n terms of the sequence. And remember, m is less than n by assumption right now. So when I list the first n terms, I will include the first m as a sub-sum. So that'll be let's see, -1 to the 0 over 2 to the 0 plus 1. Oh no, that's supposed to be blue. -1 to the 0 over 2 to the 0 plus 1 plus ... plus. And I need this to go all the way out to the nth term, but it goes out to the mth also. -1, and then it just keeps on going, to the m divided by 2 to the m plus 1 plus -1 to the m plus 1 all over 2 to the m plus 1 plus 1 plus, and then it keeps on going until it makes it out to the nth term, -1 to the n. Oh, that's not visible because of where it is. -1 to the n over 2 to the n plus 1. So there's the first one of the sums written down. Now I need to subtract the second one. So -1 to the 0 over 2 to the 0 plus 1 plus ... plus -1 to the m over 2 to the m plus 1. But now if we zoom out a little bit so that you can actually see, this red sum is exactly the same as the first m terms of the blue sum, so we can cancel them because these are all added. Oops. These are all added together and then the same thing but subtracted. So a bunch of terms cancel, and I'm left with, and I'm going to, I'll write it out with the ... dots and then I'll put it in summation notation. In general, like, you can notice all of this and put it in summation notation in your head. I'm putting in more detail than often one would. -1 to the n plus 1 over 2 to the n plus 1 plus ... Oh, nope, those are n's. Plus -1 to the n over 2 to the n plus 1. Once you cancel all of those common terms. But I can rewrite that in summation notation. Absolute value bar sum. So it looks like the superscripts, there should be a plus 1 next to that m also, run from k equals m plus 1 up through k equals n, and then it's the same thing inside of the sum, -1 to the k divided by 2 to the k plus 1. Because then when you plug in k equals n plus 1, you get the first term of the sum. When you plug in k equals n, you get the nth term of the sum. And you hit all of the values in between. Cool. So the next claim is that we can get something out of the triangle inequality. And so you'll remember in particular a while ago, as a homework problem, I had you use a combination of the triangle inequality for a sum of two things and induction to get a result. That's what I'm going to use right here. If I have an absolute value around a sum of a bunch of things that are alternating between positive and negative, if I put the absolute value bar around each of those things, then like the signs no longer fight, and so the result will become bigger. And you prove that using induction already. So there's something that you can get just out of the triangle inequality. Okay, so now we can manipulate this. Negative 1 to the k just alternates between plus and minus signs, and the denominator is just positive, so I know exactly how to deal with the absolute value bars. That is exactly the same as the sum from k equals, let's zoom in so I don't write on top of myself, m plus 1 up to n of 1 over 2 to the k plus 1. And now I just want to manipulate this, and one thing you'll notice is that thing looks an awful lot like the geometric series, or I guess a geometric sum, which is something that there is a formula for. If you don't remember the formula for it, then I encourage you to pause the video right now and look up the formula for a geometric sum. Good, you're back. Let's use that. So the geometric sum is what you would see if this plus 1 just weren't there. Well, but that plus 1 is just making the denominator bigger, so if I erase it, the denominator gets smaller, so the whole thing gets bigger. So in fact, I get a strict inequality. That sum is strictly less than the sum from k equals m plus 1 up to n of 1 over 2 to the k. Oh, so but you notice that these things have a bunch of common factors. They're all powers of 2, so they all have a bunch of 1/2s in common. In order to, I think, really emphasize, if you don't feel comfortable with summation notation, I'm going to break this back out I'm going to expand out the summation notation. So I see 1 over 2 to the m plus 1 plus dot 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 plus 1 over 2 to the n. Okay, cool. So let's take advantage of this. So I'll factor out the smallest number of 1/2s that I see in the lot of these. So m plus 1 is the smallest power I see on any of those 1/2s. So I'll factor out a 1/2 to the power m plus 1 and get a result. And so that means I need to reduce the power on those 2's by m plus 1 in each case. So there's 1 plus, the next term would be 1/2 to the m plus 2. So the next term would be 1/2 plus dot 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 plus on up to 1/2 to the n, but I need that n reduced by m plus 1. Which, that'll do. And maybe one can put this back in summation notation now. 1 over 2 to the m plus 1 times, well, oh, come on. So, what are the powers that I see on the 2? Well, the smallest power I see is 0. So it's a sum of a bunch of 1/2 to the k's. And the biggest power that I see is n minus m minus 1. So k is going from 0 to n minus m minus 1. There's a formula for the geometric sum. And maybe I'll write it down right here, even though if you didn't know it already, you already went ahead and paused the video and looked it up. But the formula for the geometric sum tells you that the sum, in particular of a bunch of 1/2, well, I couldn't write it in its full strength. The sum of x, sum of a bunch of things that look like x to the k, where k runs from 0 up to p, is 1 minus, oh, you can't see that if I do that, 1 minus x to the p plus 1 all over 1 minus x. And there are a handful of different ways of proving it. You can use induction. You can multiply the 1 minus x over to the other side and check that that equation is true. A couple different ways to do it. So, applying that formula, what do I get? Well, it looks like the x is 1/2. So this is equal to, I'll just hold on to this 1/2 to the m plus 1 times 1 minus 1/2 to the n minus m minus 1 plus 1. So that's n minus m all over 1 minus 1/2. Do you know what? This next step, we should do some simplification. In fact, let's do lots of simplification. So I'm going to put a less than or equal to sign here. In fact, maybe a strictly less than. Maybe I'll motivate what's about to happen. So yellow. So this isn't part of the actual proof write-up, but this is part of the motivation. As little m gets big, that thing is getting very small. So that piece is enough to conclude that the thing is getting small. Let's look at this remaining piece. In the denominator, I just see division by 1/2. So that's multiplication by 2. If I take something small and multiply it by 2, it's still, small. In the numerator, I see something that's basically 1. Right? I'm subtracting, well, n and m might be close, so maybe I don't know it's close to 1. But it's certainly 1 minus something. So that numerator is less than 1. So I have something small, and I'm multiplying it by something that's less than 1 over 1/2. So it's 2 times a small thing. That's still small. So this is strictly less than. I'll leave the 1 over 2 to the m plus 1 alone, times 1, because this numerator, that numerator, oh, I have this ability. This numerator is less than 1, and the denominator is 1/2. And now let's simplify that a little bit more. So that's the same thing as 1 over 2 to the n. So in that step, I use the formula for the geometric series, and I also use that 1/2 to the n minus m is bigger than 0. All right, so I have just a 1 over 2 to the power m. But this little m, by assumption, is bigger than big N. So that means 2 to the little m is bigger than 2 to the big N, but it's in the denominator. So if I replace that 2 to the m with a 2 to the big N, I'll make the denominator bigger, so the whole denominator bigger. The denominator will get smaller, so the whole thing will get bigger. So there's a 1 over 2 to the big N. But you know the game now. Once you get it down to a formula that just has a big N in it, well, now I know what to do off to the side. So here, I'll do this off to the side. I need to solve 1 over 2 to the big N equals epsilon. And there's more than one mindset that one could take here. This will be the one that will give the optimum choice of big N given this logic. But it'll also require us to know about logs, which we haven't rigorously checked that they exist. So here, I'll give you one mindset and another one. So here's one mindset. Just set that equal to epsilon and solve for big N. So I guess that's 1 over epsilon equals 2 to the big N. So the log base 2 of 1 over epsilon will be equal to big N. And let's just check what happens when, because a sanity check you should often make is when epsilon is really, really small, big N should have to get really, really big. just generally. So let's just think about what happens when epsilon is close to 0. When epsilon is like 0.00001, 1 over epsilon will get very, very big. The log of a very, very big number is still a big number. Yeah, so n is getting big. So there's one mindset. And given that trace of big N, this will be equal to 1 over 2. Oh, well. This will be equal to 1 over 2 to the log base 2 of 1 over epsilon. And you can see how this algebra is going to work out. Right, 2 to the log base 2 is just 1 over, so 1 over epsilon equals epsilon, since big N is equal to the log base 2 of 1 over epsilon. Nice. Well, I guess now that we have our trace of big N, this is always like a last step you should do in an epsilon n proof. Cool. So let's go ahead and, well, let me just make sure we have our trace of big N. So let's just read through this proof. So we've considered any epsilon bigger than 0. That was the first line. We showed that s sub n minus s sub n, by doing some work, in absolute value is less than epsilon. That completes the proof. Now, you might object that this proof uses a reference to the logarithmic function, which we haven't justified its existence. We've hardly even justified the existence of an exponential function. So here's another strategy you could use. So instead, once you get down to 1 over 2 to the big N, well, that's certainly less than 1 over big N. And this will give you a different choice of epsilon, right? You set that equal to a different choice of big N, right? So you set that equal to epsilon and you can solve. So there's another strategy. You could say, well, this is less than or equal to 1 over big N, and then that would be equal to epsilon with the choice of big N equal to 1 over epsilon. So there's always more than one way to prove a thing, but I think that's worth pointing out in this particular case. Okay, well, let's just summarize. So we've checked that for every epsilon bigger than 0, there exists a big N, such that for little m and little n bigger than big N, that difference is less than epsilon. That's exactly what it means for a sequence to be Cauchy. So this sequence is Cauchy. But a sequence is Cauchy if and only if that sequence is convergent. So that means that this sequence is convergent. Now, one thing that I have no idea about right now is what the limit of this sequence is. I know that it exists, but that's all I know. Well, now that we know that it exists, there's one way to estimate the limit, and that's just by evaluating the, say, 1,000th term of the sequence. And I've done basically no numerics in this class ever. Let's take a moment and do some numerics. I encourage you to pause, if you would like, and do this on your own. I'm going to pull up a tool for this. I'll pull up that tool. So it's going to take me too long to type, so I'm going to pause while I do that. All right, here we are. So I've inquired using a machine, asked it to compute the sum of the first 1,000 terms of the sequence. There's some notation. And I've got a total of about 0.294. And you'll notice that that is different from what appears in the notes. And that is because I cannot be trusted to actually do a computation correctly, especially with the aid of a machine. If you like, that's the sum from k equals 1 to 1,000 of the same thing. Fortunately, this is just a toy example. I didn't care about the limit, so I don't object to that error at all. So, what is left? We've used the theorem to, well, do a computation to check that a limit exists. We still need to prove the theorem. So I'm going to pause for now. I'll be back. All right, I'm back. Let's carry on. So the next thing, right, we've used this theorem to show something converges, and then made an estimate as to what the limit might be. Oh, and it's still there. That's not a correct estimate, as we just mentioned. Let's prove the theorem. So let's prove that a sequence is Cauchy if and only if it is convergent. And one direction is easy, right? Convergence is a really strong hypothesis. Knowing that a sequence converges tells you a lot. Let's explain why every convergent sequence is Cauchy, and here's how we'll do it. So I think first I want to write down a picture of the proof. So what we want is eventually to show that a sub n minus a sub m is very small. So let's just picture them as dots. A sub n and a sub m. I would like to measure the distance between them and conclude that that distance is small. Well, one way to show that two things are close to each other is by demonstrating that there exists another thing which is simultaneously close to both of them. And, well, there's an obvious candidate. A sub n converges to the limit, so I can get this distance to be small as long as little n is big enough. I can get this distance to be small as long as little m is big enough, but I'm allowed to assume that, right? I want to assume n and m are bigger than some threshold value. And then, well, what will I be able to conclude from that? I'll be able to conclude that this distance is less than 2 epsilon. But this even tells you how to fix the proof. If both of these were epsilon over 2's, which, right, I can also arrange. I can make the distance from a sub n to a and a sub m to a. Sorry, I didn't label it. I can make those smaller than any positive number I want. If epsilon is a positive number, so is epsilon over 2. So I can get those divided by 2, which as a consequence will divide that by 2. That'll complete the proof. So there's the picture. Let's just put it into words. Let a sub n be a convergent sequence. Suppose that the limit of a sub n is a. And you know that that's a reasonable thing to do. Well, you know the limit exists. And the picture that's now to the right off of the screen tells you that a will be important. I need to show that for every epsilon bigger than 0, there is a big N such that if little m is bigger than big N, little n is bigger than big N, then the distance from a sub n to a sub m is less than epsilon. Oh, apparently, so now is when I was supposed to pause and draw the picture to the right. But, well, it's still there. So for every epsilon, something happens. So the fact that there's a for all epsilon right here tells me, try to figure it out. So let's consider any epsilon bigger than 0, right? I need to prove, I need to have consider any epsilon at the start of my proof. Next, I need to come up with a big N. Well, the only fact I know is that a sub n converges to a. That's the only thing I can use to get a hold of my big N. Since a sub n converges to a, there exists some big N such that if little n is bigger than big N, then the absolute value of a sub n minus a is less than, I could put any positive number I want there. So I could put epsilon there. But instead, I'll put an epsilon over 2 there because I know that's what I'll need. Since little m is bigger than big N and little n is bigger than big N, suppose that little m is bigger than big N and little n is bigger than big N, right? That's what I need to do. I want to show that for all little m and little n bigger than big N, something happens. So I should consider any m and n satisfying those conditions. Because little n is bigger than big N, this difference is less than epsilon over 2. Because little n is bigger than big N, this difference is less than epsilon over 2. And, well, the picture on the previous page, the one that I drew off to the side, was of a triangle. So that tells me that I'm going to need to use the triangle inequality to compute the distance from a sub m to a sub n. I'll compute the distance from a sub n to a, and the distance from a to a sub m. And that's clearly equal, right? I've added and subtracted a single thing. By the triangle inequality, that's less than or equal to the distance from a sub n to a plus the distance from a to a sub m. By the line above, that's less than epsilon over 2 plus epsilon over 2, which is epsilon. And now let's just read the proof. We started by considering any epsilon bigger than 0. There it is. We came up with a choice of big N. there is some big N, so there exists some big N, such that for little m bigger than big N and little n bigger than big N, something happens. Namely, the distance between a sub n and a is less than epsilon. Thus, the sequence is Cauchy. So that was supposed to be the easy direction. Let's go the harder direction now. So let's suppose that a sub n is a Cauchy sequence. I need to show that a sub n converges. How will I do that? I'm going to find a candidate to be the limit of a sub n. And let me give you a sketch of the proof that I'll use. This isn't the only type of proof of this claim. So if a sub n is supposed to be convergent, well, every convergent sequence is bounded. So if we want it to be convergent, at a minimum, it needs to be bounded. So step one, let's show that this thing is bounded. So here is the outline. We'll show that Cauchy implies bounded. If we can do that, if we can get this sequence to be bounded, well, I know something about bounded sequences, and that is that they have convergent subsequences. They have convergent subsequences. So there's step one. If I can accomplish step one, then I can get a subsequence to converge. Ooh, but wait, that'll be useful. If I can get a subsequence to converge, well, if the whole thing converges, it has to converge to the same as the limit of this subsequence. So let's give the limit of that subsequence a name. It will converge to some number. Let's call it A. Now I know what the limit should be. If the sequence converges, it only has one possible limit. That's the only possible thing that the limit could be. So the final step in the proof will be to show a sub n converges to A, because it couldn't converge to anything else. Okay, well, there's an outline of the proof. Let's do it. So step one, show that the sucker is bounded. So this will feel a lot like the proof that we did a while ago that every convergent sequence is bounded. Boundedness is such a weak condition that we don't need to have all of the strength of for every epsilon. Let's just take a single epsilon. I'll take epsilon be equal to 1. Well, because the sequence is Cauchy, let epsilon be equal to 1. Maybe I'll... Because a sub n is Cauchy, it follows that there exists some big N, such that if little m and little n are bigger than big N, then the absolute value of a sub n minus a sub m is less than 1, because that's the choice of epsilon that I'm taking. I know that this is true for every epsilon. 1 is bigger than 0, so that in particular is true. All right, well, now I'll make some choices. I'll pick one fixed number that's bigger than big N, namely big N plus 1, and then I'll consider any little n. So it follows then that for all little n bigger than big N, the distance from a sub n minus a sub big N plus 1 is less than 1. So, but I want to get bounds on an. So, well, you know what I'm about to do. I'm going to solve this inequality for a sub little n. And, well, you already know what I'm going to write, so I may as well write it. So that means that a sub big N minus 1, here we saw a sub big N plus 1 in the subscript minus 1 is less than a sub little n is less than a sub big N plus 1 plus 1. Aha! That seems useful. So I've almost found bounds. It sure looks like this is a lower bound. It sure looks like that is an upper bound, but I don't have it for all n. I just have it for all little n bigger than big N. So let's describe why this nonetheless results in a sub n being a bounded sequence. So, well, let's do it. Let's see, the set a1, a2, dot, 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 a sub big N is finite, and every finite set is bounded, and so is bounded. Let U and L be upper and lower bounds on the set, on that set. And I only said a few words, so I'll be a little bit unrigorous in that I'll leave just a gap right here. The max between U and a sub n plus 1 is an upper bound for a sub n. The min between L and a sub n plus 1 minus 1 is a lower bound. Cool, so there, the sequence has an upper bound, it has a lower bound, so it's bounded. So a sub n is a bounded sequence. What does a Bolzano-Weierstrass stress say? Well, you know what Bolzano-Weierstrass stress is. It says that every bounded sequence has a convergent subsequence. So a sub n has a convergent subsequence. So let's let A be a subsequential limit, which exists if it has a convergent subsequence, and let's let a sub n sub k be the subsequence, a subsequence of a sub n, which converges to A. Saying the is very long. There's not a unique convergent subsequence, there are many. So let's prove that a sub n converges to A. That's the only thing it could be. Right? A sub n couldn't converge anywhere else, so its only choice there is converge to A or diverge. We want to show it converges, so here's the candidate. So let's do it. And this will be another epsilon n proof. So there are two facts I know right now. I know a sub n sub k converges to A, and I know that a sub n is Cauchy. So let's try to play this game. So let's see. There's a sub n. I would like to get it to be close to A by taking little n to be big enough. And well, at the very least, things that look like a sub n sub k, I can get to be close to A. If k is bigger than some threshold number, I bet I'm going to call it n2. Now, so I can get this edge to be small. This edge, on the other hand, well, this is a term of the sequence, so I'll take little n to be bigger than some threshold big N. That comes from the fact that a sub n is Cauchy. As long as n sub k is also bigger than that threshold number, I can get this side length to be less than epsilon if little n is bigger than big N1 and n sub k is bigger than big N1. And I haven't told you what these big N1 and big N2 are, but it will come up in a moment. So that will allow me to conclude using the triangle inequality that this side is less than 2 epsilon, and so what'll I do? I'll divide all the epsilons by 2. So there's a sketch of the proof, not the actual proof. I don't ever want to see in your homework something that looks like this. This isn't part of the proof. This is part of the scratch work that you do in advance. I never want to see that. Ooh. Oh, I can have multiple pointers? That's interesting. Okay, so let's do it. So let's consider any epsilon bigger than 0. Because a sub n is Cauchy, there is some threshold value n sub 1 such that for all, not just n, but m and n bigger than big N, the difference between a sub n and a sub n is less than epsilon, and that could be any positive number. So I know already that I need to divide it by 2, so I'll divide it by 2 right now. And the proof, check notation really quick. Pretend that that's not an n sub 1. So what have I done? I've just crossed out that subscript 1. In this last step, in this claim, I considered any epsilon bigger than 0. I came up with a choice of big N using the fact that it's quite nearly done. This won't take long. There's a problem here. I'll be back. All right, awesome. If you're curious, the trouble was that page 3 was repeated twice. Well, page 88 was repeated twice instead of going on to page 89. All right, so I've written down what we get out of the assumption that a sub n is Cauchy. I also know that the subsequence a sub n sub k converges to a. Because a sub n sub k converges to a, there is some threshold number big K, such that if little k is bigger than big K, then the distance from a sub n sub k to a is less than, need this, epsilon over 2. Cool. All right, so I get that as soon as little k is bigger than big K. Now there exists a trace of big K such that both simultaneously little k is bigger than big K and n sub k is bigger than big N. It's a strictly increasing sequence. So let's consider that choice of little k. And, well, remember, I want to show that a sub n converges to a, so I need to assume little n is bigger than big N. There's my assumption that little n is bigger than big N. I now have the distance from a sub n sub k to a sub n is less than epsilon over 2. And that's true by the numbered equation inequality, 2.5 on the previous page. I know that little n is bigger than big N and n sub k is bigger than big N. So this distance is less than epsilon over 2. Now, I also know that little k is bigger than big K. So this difference is less than epsilon over 2. So by the triangle inequality, the difference between a sub n and a is equal to the difference to a sub n minus a sub n sub k plus a sub n sub k. I'd add and subtract the thing that I know is simultaneously close to both of those things. That's less than or equal to absolute value of a sub n minus a sub n sub k plus absolute value a sub n sub k minus a. That's less than epsilon over 2 plus epsilon over 2, which, hey, that's equal to epsilon. So let's just summarize. I also came up with a choice of big K, but that was something that I needed inside of the guts of the proof, but it's not part of the conclusion. I considered any little n bigger than big N. See, right there. I considered any little n bigger than big N, and I concluded that the difference between distance from a sub n to a is less than epsilon. So, thus, a sub n converges to a, as this claim showed. Well, notice that claim told us that a sub n converges to a. I don't care about a, I just care that it converges. I considered any Cauchy sequence, I did some stuff, and I eventually showed it converged, and I even said where it converged. That completes the proof. Nice. So that ends this lecture.